Good afternoon, everybody. Thank you very much for the invitation. It's my great pleasure to give the presentation on federal learning and analysis in mobile edge network. And this is done by many of my students and collaborators, and thank you for NSF and Toyota. And here is the outline. First, we have the background, and then we try to study the federal learning from the machine learning and optimization point of view. And then we talk about two examples in federal learning and two examples in federal analysis. Okay, and finally, we have the open problem and the conclusion. And for the background, there are many billions of data of phone and IoT generated every day. And the data, instead of calculating in the core or the cloud computing, which is far away, the data is more and more calculating at the edge because it can improve the latency. Think about this data center in Guizhou. Okay, how far away, okay, it is, and what is the round trip delay. And so that we can have a better work offline, better life, and also can protect the privacy. However, what to learn and what to analyze become more important. So this is a motivation for this kind of edge-based federal learning. So from the machine learning point of view, okay, what is federal learning? So at the beginning, the server already trained some kind of clustering, and suppose we have a linear clustering, but obviously it's not need to limit it here. So this is the initial kind of training. On this side, we say this is apple. On this side, if we get sample, we say it's banana. And then we broadcast that kind of data to the different client. And for the different client, they will collect the data and then do the label by themselves. And those white point is a new label. And after the label, okay, everybody try to update their kind of clustering method. And then this is a new clusters for the new cluster method for the new kind of based on the new data. And so in the next one, instead of sending all the data back for the server to recalculate the gradient, the new clustering, they can report this kind of cluster result, this cluster gradient or this black lines back. And then in the server, instead of getting all the data, which kind of a privacy problem, they just get all this kind of a gradient update. And so in this case, okay, they will adjust and then broadcast back to this client. So those clients with a newly updated gradient, it will not only contain the information that it has as its only data, but also the others kind of client kind of information and the data training result. So by doing this, okay, we can reduce this, we can protect the privacy, and also we can reduce this signaling between the different client and the server. So in this case, that's the major motivation of machine learning. Okay, the advantage is that it's an effective way to tackle the RID data. And for example, okay, for different server, just like this 5 blind people to touch the elephant. And then somebody touched the trunk, somebody touched the tail, somebody touched the leg, and they will have a different description about the elephant. So, but by using the federal learning, okay, those people's kind of information can be aggregated together. So in this case, okay, even though only each client only see part of the story, but the whole server can have an overall story. So this is a good thing. And second thing, I already mentioned, the communication cost, okay, is reduced because only this kind of gradient is reported. And also the privacy is also protected in the sense that the real data is not transmitted. So there are a major challenge, again, is still the non-ID unbalanced data. And some users have more data than the other, limited communication, and the massive distributed. So overcome this problem, there are many kind of approaches. And here from the second perspective is from the optimization perspective. And essentially, federal learning aims to collaboratively obtain the global machine learning module from end user. And for individual I user, they will get the data Y and then they have the label xi, and then they train their own kind of gradient omega I. And then this is the server will just aggregate their kind of overall weight according to the total size, they weighted by the total size, total data size. And then finally, okay, the total objective function is look like this one to minimize the overall distortion. And this is the number of client. And let's remember that, okay, unlike the FVM, which is a convex optimization, and for deep learning, it's typically non-convex. So basically, the overall objective would look like this one. The problem for compared with the FVM, this objective function f is sometimes no closed form solution. For example, okay, it's just a black box. Okay, you don't even know the shape, and most of all, because deep learning is a nonlinear filter, nonlinear structure. So in overall, it must be a non-convex case. So you will fall into many kind of local optimal. So this one cause a significant challenge on this deep learning based one. And so in this case, we have the gradient method starting from any point, and then we try to update it according to the other direction of the gradient, so it will falling down to the local minimum until kind of convergence. I mean, some kind of stopping criteria is satisfied. And the problem is that, okay, it's usually kind of a very slow convergence. So in order to speed up the convergence, okay, we use this kind of a stochastic gradient descendant. So basically, okay, we have a learning rate, and this is a kind of for each individual user. And then, okay, we pick a small subset or mini batch of the training sample, small subset, and then try to update it. So we, instead of waiting for all this data client to report to us, okay, we just pick a small cut subset, and then we begin to update. So in this case, okay, we can update this kind of result very quick, okay. And so in other words, whatever data you have, we just update, and then we can wait for the rest to get the data. And then we have this federated stochastic gradient descendant method. This is typically for federated learning. It is a baseline. So we have one approach that everybody just wait. Everybody for the different time wait is just kind of average of this kind of gradient, average of the gradient. And in the second approach, each client continue to calculating this kind of their own weight, and then after a while, okay, they will kind of they will kind of update together. So typically, the second approach will save more energy for that. So how could I say that? Okay, the first one, okay, they will update it each time for everybody's kind of weight. And in the second one, for example, I will not talk to my student every day. This is the first solution. Instead, I will talk with them maybe a week or maybe 5 days. And after they accumulate, they are kind of, accumulate for a while, I will try to kind of collect the data, try to have intermediate meeting so that, okay, we will correct my direction and then give them the update about the guidance. So in every week, they will have an update. In the middle, they update themselves. So by this way, we save a lot of energy. Yeah, because okay, I also have a bandwidth limit, and there's no way I can talk with my student for so many times. And the further learning, okay, deal with limited communication. So basically, okay, this is a global training, global distributed training with a communication, dominant communication cost. So in this case, okay, we can use this kind of try to increase the local communication and then try to save this kind of communication cost for this, so as to achieve the overall performance. And here is this kind of a final average kind of a summary. And then each server try to update themselves themselves, and then whenever their bandwidth is available or whenever there's a kind of communication time, and then they will report to this kind of server, and the server will average them. Yeah, for example, sometimes I'm very busy, and but my student will try to find me. I mean, before COVID, okay, try to find me whether or not my office door is open. It's open, that means I'm open to discussion. If it's closed, that means basically I'm currently busy for that. So basically they will find this opportunity to update their gradient to me so that I can average them and give the best gradient to the group. Okay, here is the overall kind of a federal learning kind of a federal learning kind of a solution, federal average solution. And the overall at first model is randomly initialized on the central level. And for each round, a random subset client are chosen. Each client perform local gradient update, and the server aggregate the model parameters submitted by the client. So this is basically the baseline for the federal learning. And here we use the first paper we have done is based on this federal learning based mobile edge computing, and we use for the Toyota for this kind of AR, VR kind of a signal. And there's a central cloud. And then for the different clients, they have this different AR, select the devices, and then try to download the naive module. And then for the local update, they use this kind of training, and then try to do their self-training, and then report it back for the global aggregation. And then after getting the overall kind of updated one, they will report it back. They will send it back to the devices. So by doing this one, okay, this is the recap of the federal learning. And we have implemented several years ago for this Toyota AR. And anyway, okay, let's talk about some kind of examples that are different from the classical approach. And the first example is unsupervised learning for unbalanced data. So previously, for further learning, everything is supervised. You have to tell that, okay, the label for each user, what is going on, so that they can update their gradient. However, beyond supervised learning, there are unsupervised learning. So for unsupervised learning, okay, the tasks are being implemented within the federal, we want to say whether or not tasks can be implemented by the federal learning network. The challenge is that the federal learning training reduces significantly when the data is ununiformly distributed. So in other words, okay, if somebody have more data and somebody have less data, this unsupervised learning can be not good. So compared with the supervised learning, we will get unsupervised learning. So this is the unlabeled data. And then the goal is trying to find this kind of a centroid of the cluster. And then, okay, also this, which is MK. And also XJK basically means certain point, J belongs to certain point J belongs to mu J NK basically means, okay, certain point belong to a certain cluster, certain point belong to a certain cluster. So you can see that, okay, this is a mixed integral programming compared with this supervised learning, which is just a continuous optimization. Here we have the integral. Integral here basically tell, okay, which point belongs to which cluster. So you can see this is a very significant difference from the classic federal learning. And then we try to have this methodology of dual averaging. So the first one, we have the data labeling according to certain heuristic. And then we have the centroid computation. So this is a kind of basically modified EM algorithm. EM algorithm where this, there are two types. One is for expectation, the other is for maximization. Okay. And here is the example. Okay. And for agent one, they see those clusters. Agent two, they see the other side of clusters, and they are quite unbalanced. So the key question is that, okay, how could we overcome this unbalanced one to achieve the overall goal, as if the server see all the data and do the classic k-mean or EM algorithm. But here, okay, for different agents, they will have their own data, and then they don't want to share with each other. So in this case, how could they do? Okay, And here we use some kind of weighted computing with a self-organized map. At the beginning, okay, the different people this is our different people, they will have this kind of overall weight. And then by iteration, this kind of weight map is a kind of changed so that, okay, the different people will kind of have different weight for their opinion. So in other words, okay, those agents will have the more kind of weight in this one, this agent will have more weight in this area. So by doing this one, we can converge the solution. And here we show you the simulation result, and this is the iteration. And on the bottom is this kind of suppose everybody know all the result, and then this is a kind of case. And then, okay, with this kind of with a distributed solution, we can show that, okay, it's close to this kind of global information. If you get all the global information, K-mean, well, compared with the other algorithm, we have a better convergence solution. So basically, this is not unsupervised learning story. And another point is matching theory with low latency and multitask federated learning. So what is a multitask? The previous federated learning, everybody have this just one choice. Okay, we want to implement this task or the one task only. However, in the future, every devices will have their own preference and their own ability due to the mobility and also other situation. And for this kind of mobile edge node, they will have the different task. And then the key question is that, okay, those devices will select the right kind of choice for them for this kind of report. Well, the server, the edge will also select the right kind of devices to implement their task. So in this case, okay, they become a matching problem. Okay, so basically, okay, this is a kind of a thing. And also we want to say, okay, the information to do this matching, we want to have a locally, and we don't want to have the global information to be exchanged to do optimization, because otherwise the complexity is far too big. But we want to have the low complexity so that we can match the edge server with the different devices for the machine learning. So how could we do? And then here we talk about the matching game. The matching game is basically, okay, it's a Nobel Prize winning kind of algorithm that have been developed by the Shapley in UCLA, Professor Barney in UCLA. And the most simple one, okay, is stable marriage. And suppose we have a set of men and a set of women, and who want to match together. You'll see that this is very much look like the edge server and the devices that we are targeting for. And then we have the preference list. So basically, okay, and the one of the devices prefers the other. Okay, prefers one device. One of the servers prefers this devices than the other, and vice versa. And for man and woman, okay, they obviously have their kind of preference. Okay, and we have the blocking pair. But what is the blocking pair? The blocking pair means that, okay, a man prefers a wife. But the man prefer a wife than his current wife. And this wife also prefer this man than his current husband. So obviously this is not quite harmonic, right? And then those two couple will divorce, and this man and this woman will marry together. So this is called blocking pair. And for stable matching, the basic story is trying to finding this kind of a matching without a blocking pair. So basically, nobody have the incentive to divorce. So this is the objective function. And you can see this is different from the global optimization, global system objective. But because everybody want everybody want to have this preference, have his partner on the top of the preference list. So this kind of stable matching must achieve kind of a near optimal solution. Moreover, such kind of things, okay, it's not centralized control. Everybody just searching for the nearby one. And so this is kind of low complexity. And here we use a Gale-Shapley algorithm to find a stable marriage solution. So what is the Gale-Shapley algorithm? So here is the example. We have a set of man preferred the set of another woman. And then this is Adam's kind of preference list. This is he preferred Gita better than the hierarchy, better than Irina, better than Fran. So obviously he tried to date Gita first. And Bob, like Irina, and Cars, also like Gita. And then Gita think Cars is a tall, handsome, and rich. So Gita damn Adam. And Adam have to find the second on the list. And David also tried to PK with Bob, and Irina dumped Bob, and Bob tried to find the second preference list. So you can see that, okay, that we, in this case, we reach a kind of stable marriage, and nobody want to nobody want to divorce or separate. So this kind of things is very, very fast. Okay, this one is converge very, very fast. For my PhD student, after they come to US, within 1 semester, they converge. Okay, so the problem is that, okay, what is this kind of incomplete information? So, I mean, this preference list is incomplete typically. Yeah, first, okay, I don't think I need to have a kind of preference list of 3.5 billion women, right? That is too long, yeah. So in this case, we must have the incomplete list. And also for the devices, millions of devices and thousands of edge computing, they must also have an incomplete list. So here, the key story is we try to kind of implement the matching with incomplete list. And for detail, please see our paper, which I think I put here, maybe. Yeah, we put here. Okay, and then, okay, here the results show that, okay, with this kind of number of edge nodes increase, and we can reduce a lot of kind of latency. And while the number of user increase, okay, our performance is also better. So in this case, we can see that, okay, proposed distributed solution, distributed game theory solution with low complexity, indeed, okay, have a good performance. Okay, so those are the variation of the federated learning compared with the classic federated learning. And we have the unsupervised learning, we have the multi-objective one. And now, okay, things have move on from the federated learning to federated analysis. So what is the federated analysis? So here we have this kind of different mobile, try to see the out of dictionary word. And also we try to see, okay, for the different devices, they want to have the modal efficiency. And also for the popular sound trend, they have the different preference. And then, okay, for further analysis, it's practical of applying data science method to the analysis of raw data that is stored locally on user devices. So what does this mean? For further learning, the server do not do anything. Okay, they do not do too much complicated thing. They only do the average of their weight and so on. Well, that is too simple. How about the data become more kind of assorted? And then for the server, what they can do is that, okay, they can do a smart one. Beyond this just average, they can do the data analysis. For example, I have the different opinion from the different kind of, I want to recruit somebody, and I have the different opinion from the different sources. And then I try to use my thinking or analysis to average all this kind of different opinion so that finally we can select the right one. So this is a kind of a difference between the federated analysis and federated learning. And the terminology inside are derived from the client and sent to the server. So instead of just average, they give an insight. And aggregation are performed by the server for global knowledge construction. So in other words, okay, so for further learning, they are still reporting the gradient. And such kind of gradient is, the server is just an algorithm. Well, for this kind of further learning, from this kind of federated analysis, it is an insight that kind of reported from the server to the aggregation. So instead of the real data or instead of just a gradient, they report an opinion. In this case, okay, the server can be aggregated together. And So, for example, okay, let me give you an example. This Liu Bei, okay, when Lu Bu got caught by Cao Cao, okay, Cao Cao asked this Liu Bei's opinion. So Liu Bei, instead of giving the real answer or this kind of gradient, Liu Bei report that, okay, do you remember that Lu Bu killed his father? And then obviously this is just opinion. And then, okay, obviously, okay, this information is delivered. Okay, that's just an example. There's a characteristic, no raw data exchange, and focus on popular level knowledge, and they can have privacy guarantee because this is just my opinion, okay, and interactive and non-interactive cases. So for further learning and further analysis, the goal is to train, for further learning, the goal is a training machine learning method. For the further analysis, they can have this non-training task like the data size. And for further learning, the aggregation approach is just average. And for the further learning, it's really task dependent. They can have a tree, Bayesian, MPC, whatever the case. So it's a more data analysis. For local insight, okay, for model learning, it's just a model of weight, and further analysis is more kind of task dependent, and partial information, distorted information, and so on. So you can see that, okay, further learning becomes more kind of sophisticated with a more deep data science. And here we try to use this data analysis for this data mining. And for distributed data mining, the raw data transmission is a redistribution is assumed. And the further analysis stay where it is originated. And the client and server basically distribute the data mining is trusted. Well, for this further analysis is kind of untrusted. And then we have the data devices heterogeneous, and little is concerned, but for further analysis is focused. So here in your paper, which is published by IWQS, and this is a FedACS, a standalone federal analysis instance assisted some other federal task. And so basically, okay, we measure the data heterogeneous or skewness and create a client pool with low data skewness. And when assisting with the federal analysis, we can reduce 65% of accuracy loss and also speed up 2.8 times. So here is basically, okay, the federal analysis kind of using for distributed data mining, okay. And this is the first example. And the second example is a federal analysis abnormal detection for local model poison attack. So for this local model poison attack, it's a threat model. The attacker can manipulate the share of local model and not local data during the process of federal learning. So basically, okay, if you remember this Microsoft open this kind of online character, I forgot the name, and try to chat with the different people. And then by chatting with them, they can become more and more human. And this is open to all the human beings. However, only after half day, they shut it down. And this is several years ago, okay. Why? Because you know that, okay, when you look like this, those people, okay, online, okay, are they real common people? In Chinese words, okay, 网络喷子, okay, are they really kind of I mean normal? And matter of fact, they are sick, very sick, okay. And then within half days, okay, this Microsoft machine learning girl has been trained to some kind of only speak dirty word or something like that. They have to unplug it, okay. So this is a kind of local model poison attack, and the impact is slow down the convergence rate of learning process and degrading the prediction accuracy of learning model. Yeah, obviously, okay. Somebody give you the wrong advice, okay. And the most different methods are passive. So treat the normal local data and the poison local data indiscriminately, such as those two methods. It cannot eliminate all the poison local model. That training performance is affected for a certain degree. The accuracy and the learning model is reduced. So here, what we want to do is that, okay, when we do this kind of data aggregation and broadcast to global broadcast, and then for the local model training and data aggregation, some of them have the malicious, and so that, okay, those convergence will be much slower. And this paper is almost appear in JSAC. And here we use a federal analysis to proactively defend such kind of thing. So the challenge is that, okay, the data heterogeneous caused by the federal scenario increase the difficulty to the abnormality analysis. So here in the data analysis part, in this kind of server part, we have the abnormal detection module to identify the potential malicious local module and update with a little weight. So if you are kind of say some kind of extreme things and nobody believe you, okay, you will have very little weight. And then we have this kind of allow greater compatible with various abnormal detection algorithm. And here for simplicity, we use the SVM. And after that, okay, even though that, okay, you say something, maybe you know that we need to worry, okay, we need to worry in the sense that sometimes you're reporting something which look absurd, but doesn't mean that you are lying. Maybe it's true. The other didn't observe yet. You are the first people who report that. So instead of giving you a little weight, we try to have the verification module to request encrypt the local data from this potential malicious node. So if you claim that, okay, show me the proof. Okay, maybe this guy can send you some kind of WeChat history or some kind of video, a CCTV video camera, and using the encrypted one. So by doing this one, okay, they can ensure the privacy. In this case, okay, the central server collect all those data and then try to make a decision whether or not the claim is right or not. So basically, there's a verification module. And finally, we have the abnormal removal. So if you can verify yourself what you're treated right, we will give you a high weight. Otherwise, you are just completely bullshitting. Okay, and in this case, we will remove you from this account. And basically, for example, with this Tencent, okay, for the group, sometimes they remove certain people from group, right? What's their algorithm? And also they have auditing, right? They will audit, which is basically the second step. They will ask somebody to read through what it is discussing and to make sure that, okay, I mean, whether or not it's a real bad thing or not. Okay, so this is basically federal analysis. And here we show you this example. We have the accuracy, and so basically proposed method outperform other defense mechanism, and the performance gap is within a very small one. If we assume that, okay, there's a genius aided, so basically it's genie aided, okay, the solution, and then we lose a very small amount, okay, compared with that. And for robustness, okay, remain nearly the same accuracy when this kind of attack from 10% to 40%. While the other, due to this kind of look like a Byzantine attack, okay, and then okay, their performance will significantly decrease. Well, for us, okay, we can be more robust to this kind of up to 40% of the attack. Okay, and here we show you these two examples, and we have some open area in federal learning, like the optimization algorithm for federal learning, particular communication efficient algorithm, and the approach that can scale federal learning to a large scope, and novel application of federal learning beyond the current one. And not everybody have the same module. So I mean, you train like this one, I train the other way. Okay, for bias and fairness in federal learning, which is very important, and this National Science Foundation have a lot of effort for the fairness in machine learning, and enhance the security and privacy for this kind of federal learning. And the conclusion, the federal learning will be a major part of the learning paradigm, and this kind of mobile, it can be mobile massive decentralized natural writing partition. these are available for distributed client. There are a lot of communication can be a bottleneck, and we have also have the privacy concern. And we explore the different type of this federal learning and federal analysis in various network. We give you the problem formulation. We give you this kind of um, this problem specific solution, and we try to link this machine learning, computing, communication, networking, all together. And also the research is moving from the federal learning to federal analysis. And finally, okay, let me give an advertisement for our lab. This is our lab, and this is our lab website and my website. Except for study, we do everything. So I hope the COVID, okay, will end soon, and so that you can visit us, okay, in the future, and we can explore the different research together. And finally, thank you very much. And Houston, this is Houston.